Hello and welcome to today's Saratech enablement session. My name is Andrea Hall and I'm the Customer Relationship Manager at Saratech, and I'll be your host today. Presenting, we have Mikhail Bondarenko, who is a manufacturing engineer here at Saratech, and he'll be talking to you about hybrid applications in additive manufacturing. These CES sessions run about 30 minutes each and are all recorded and posted to our Saratech YouTube channel. CES stands for Customer Enablement Session. Make sure you check out our past sessions at our YouTube channel. Twice a month, we meet right here to learn about tips, tricks, new and old features that'll help you with your everyday tasks. This is an open forum, so if you have any questions or comments during the presentation, please type them in the chat box or the questions box over to the right, and I'll gladly interrupt Mikhail and let him know about your comments and questions. And with that, I will pass the baton over to you, Mikhail. Thank you.
Thanks, Andrea. And thank you all for joining me. I'd like to go over a little bit about myself. My name is Mikhail Bondarenko, and before joining Saratech in 2014, I was previously in the biotech and life science industry, working in various projects that involved robotics, automation, and additive manufacturing. Working with Saratech, I've advanced my skills to combine CAD and PLM applications and tooling design for various projects in the aerospace industry, which focus on additive manufacturing as a main source of design and production. I'm excited to share some of my knowledge on advancing existing processes of manufacturing with additive equipment, and here are the items I'll be covering today. Hybrid applications. I'm sure everyone here has heard the term hybrid car, hybrid species, hybrid food, but what is a hybrid application? Well, we're going to talk about that today and how using the same certification process that has been around manufacturing for years can be incorporated into the shortcuts that equal quicker and better production life cycles. We'll also cover the differences between today's technologies based on ASTM standards and how our products and services can help you. First off, let's talk about Saratech a little bit. As Saratech continues to rapidly grow, we want to make sure that our customers and our new customers understand what Saratech is about and drive the benefits of our partnership, what we do and why we do it. We provide engineering and manufacturing solutions that include product lifecycle management, software, engineering consulting services, and manufacturing hardware. Saratech team helps customers optimize their engineering and manufacturing process by providing extensive product development expertise and technologies. We're not just a company that sells machines or equipment or whatever else. We're a solutions company. And I'll briefly go over what hardware solutions we provide. So here at Saratech, we have the Saratech additive ecosystem. It's, let's just call that a trademark thing. But we have selected these manufacturers because we feel like in tooling, one size doesn't fit all, whether you need continuous fiber embedded nylon to fast production cycles, or maybe your project needs a life-size model, you need a car door, or lenses that you can project through, or even automation-driven metal manufacturing. Everything that you see here has a core benefit and can be used to advance or maybe speed up the manufacturing time and automate the process. We work closely with Universal Robotics, which provide cobots or collaborative robots to speed up additive manufacturing. These collaborative robotics allow you to remove parts from machines, start new prints, or move parts to a post-processing station. Plus, they never complain, get bored, or quit without notice. We also carry post-process. They are the leader in automated support removal and surface finishing. Again, all of this equals out to designing and getting a part to end use faster, or a prototype in your hands. Here I have a diagram of 7 different types of additive technologies. I'm sure you've heard some of them, but we have extrusion, powder bed fusion, vat polymerization, binder jetting, material jetting, sheet lamination, direct energy deposition. I'm sure that's an earful to hear, and I'll stick to the ones that we have selectively chosen to be the best solutions for existing processes. Now, I'm sure all of you have heard about extrusion, so let's talk about that a little bit. also known as FFF, or the term trademark FTM, just like it sounds, and it extrudes a hot filament onto a bed and creates a shape. Think a little bit of a hot glue gun that a child uses. You extrude the material and you get a 3D shape. We have powder bed fusion, which covers a couple of different technologies, but the main basis is that either uses a direct laser or on a powder, fusing it together, or heat lamps that fuse material that absorb or deflect energy in a pattern that's sprayed to create layers of a part that fuse together. And again, this is, per layer, once it fuses, you have a solid model, and so you have a 3D part. We'll move on to vat polymerization. Known as SLA, it's a liquid polymer resin out of which the model is constructed layer by layer, and a ultraviolet light is used to harden or cure the resin where required, also equaling a 3D model. I'm sure you've seen it in different types of images and conventions, but it looks like form grows out of a liquid bath. All of these technologies are part of the ASTM additive manufacturing standard that classify their process and determine exactly what they do. And now, what are hybrid applications? Let me move on to show you. Well, so a lot of people think, what is a hybrid application? They have different meanings, they have different words. Well, I've made this diagram here that you can see above, and hybrid applications are the joining of different types of manufacturing processes to develop and create a single solution or product. But what does that mean in additive? As we previously discussed, there are many types of equipment. The outer circle I've created represents traditional manufacturing. From designing a part, you think, how do I make this into a reality and have it fit, function, and perform to the specifications that I require? My first thought is, let's go CNC it, but that takes a couple weeks. And then I go, well, let's go make a mold because, injection molding is quick. Oh, wait, I have to go CNC it, and that takes a couple weeks. CNC is great. It's an amazing technology, advances every day. I'm sure, there are many operators out there coming out with little tricks and tips on how to make things faster, but at the end of the day, they're all used up. And what I believe is if someone can make a hybrid car that uses gas and electricity to get further, then why can't we use existing technologies that are proven and marry them into something new that doesn't need the red tape of recertification, which leads us to the rest of the cycle. You have sacrificial tooling, you have molds, you have MIM, which is metal injection molding, material cores. These are all standards of the industry that can be utilized with additive manufacturing in different ways that people just don't think of right now. So you can see the images above. For composite manufacturers, additive manufacturing can fundamentally change the procedure for creating complex, hollow composite parts. Traditional composite manufacturing techniques work well to produce basic shapes with constant cross sections. However, complex composite parts with hollow interiors present unique manufacturing challenges. Internal tooling, which I'll refer to as a core, are used to create the hollow features in a structure depending on the geometry. Some internal tooling can be easily removed after molding. However, any configuration that traps the core inside requires sacrificial tooling. The material you see in the above image can be dissolved once the composite is wrapped and cured. And that leaves you with a final product that you can use. And you can see the different stages in the image as the part is printed to where the sacrificial tooling from the inside is removed on the fiberglass exterior. The part you see here at the bottom was created by an FTM and took about an hour to print and additionally 4 hours to machine, then subjected to an autoclave with temperatures as high as 350 degrees and pressures of 90 psi. This was part of a Boeing spec process that is used to cure aerospace grade composite parts, and traditionally the lead time is as much as 14 weeks. This process, which is used in additive and subtractive technology, significantly reduces manufacturing costs, energy requirements by accelerating production times. Then we have metal injection molding, also an industry standard. It's the most common manufacturing technology for large-scale production of plastic parts, which lead to metal parts. By mixing metal powder with a binder the advantages of the technology can also be utilized for metal components. You can see the process here as it's moved along to produce a sintered part, which still may or may not need to be machined. And even though this is a proven and certified technology that empowers quick and easy production of metal parts, it's only once the mold is done. I don't show that process here, but as you can see on the fourth image on the top, injection molding, you have to CNC that mold. And going back to CNC, it takes a lot of time. Now, I'll show you a hybrid application that uses FDM and MIM to create a part that can be designed without the constraints of traditional manufacturing and solves an industry problem of long prototype processes and waste of material. So this is a kind of a hyped word right now, but as you can see here, compared to traditional MIM technology, this is a Mark Forged Metal X. You design the part, you print, debind, sinter, and now you have a cast metal part. Compared to the previous process that you just saw, this is 5 steps. You don't have to CNC anything. You have a metal cast part at the end of this process. And the metal powder is combined with a binder and extruded onto a print bed. Just like typical FFF or FDM 3D printing, when complete and washed to remove the binder and then sintered in a kiln, the sintering process gives you a 3D printed part that has exceptional mechanical properties in all directions, similar to a cast part. At the end of the design process of this, you have complex designs with topology optimization, lower weight, and a stronger structure. So let's talk about these parts a little bit. As you can see in the top right-hand side, you have a topology optimized part. It's been reduced from traditional CNC manufacturing all the way through a design process that removes material and optimizes it for 3D printing. This is something that many different softwares, but specifically NX, is capable of doing. And then you have in the bottom right, this is an internally optimized part with honeycomb structure. Typically, the honeycomb structure is introduced to increase strength and material properties. But these aren't things that you can do with traditional MIM or CNC manufacturing, which we go back to the Metal X. It's a new and old type of hybrid model that allows you to create these parts that aren't available before. And from this, we'll move on to the next type of hybrid application. SLA and Casting Applications. This is a mesh of 3D printing and injection molding. Parts created with this process have a similar characteristics of mass production molded parts. They have all the details of the final parts as well as great accuracy and aesthetics. You can combine them to have desired mechanical and thermal properties of production grade materials, and the process has been proven invaluable to test out rubber parts and save on costs compared with machining and aluminum prototyping. Another advantage is that there are changes that need to be made, and you can just update the design and print a new SLA mold, and the new parts are ready for testing in a couple days. You can do cast urethane, silicone, the material properties are many. And what does this solve? This solves the fact that you can, at the end of the day, have a process that's already been certified. These aren't new things. These are just used in different ways to advance your manufacturing process. Electroplating. Some people have heard about this, others haven't. So I'd like to touch base on electroplating. A lot of people didn't quite understand in the beginning of how electroplating kind of ties in with 3D printing. Well, a lot of parts that come out of 3D printing have surface imperfections, like any part. You know, even a CNC part, you have to do a second post-process on it. You have to do sandblasting. You have to change surface. You have to paint it. Well, it's no different for 3D printed parts. To have an electroplated part, it's a process that adds a thin layer of metal to a metallic object. At a basic level, it consists of dissolving one metal in a solution and subsequently attaching it to another metallic surface using an electric current. The target surface must be able to conduct electricity. So raw parts can be electroplated, and that'll give them the desired physical properties. But due to the initial, due to the initial, lost my train of thought, process for electroplating, it'll change the roughness of the part. And that may not achieve the look or feel for the applications. For example, if you need a mirror surface, or if you needed like a different type of surface, right? You need a smoother surface. The process I've defined here, as you can see from the images of the HP multi-jet fusion parts, will allow the customer to have a mirror surface finish and a roughness average of 0.04. So take a look at the graph into consideration. You can see that between a raw mechanical primed and electroplated part, the roughness variation changes from 11 microns to 0.7 to 0.2 to 0.04 of an electroplated mirror-like surface part. And this process enhances the 3D printed parts. So again, we go back to surface finishes of different types of materials and surface finishes of different type of parts. You can achieve the surface finish that you need in the process that you want. And jet metal technology. Similar to electroplating, this was developed to add a thin layer of silver to a surface which makes the surface conductive. And just as electroplating needs a conductive surface to prepare it, it consists of spraying 2 water-based solutions, an oxidizer and reducer, with standard painting equipment. It can be used to selectively add metal to only one zone or pattern on the part surface, and in the end you get an electroplated part which could be made in FFF, SLA, or SLS technology. Whether you're looking for a reduced roughness average or a chrome finish, this application uses 2 technologies that are proven to fast track the certification for production tooling, and end-use parts. And this ties into your manufacturing process by allowing you to use 3D printing in the same aspect that you would for other types of machines and products. It just allows you to enhance your products. So I hope this webinar was informative on how some existing applications can be used to innovate and create products in new ways with new technologies. And that by having a different perspective on combining additive and subtractive manufacturing tools, that can help you find a better solution. If anyone has any questions, please feel free to post them in the comment section, and I'll have Andrea take over from here. Thanks for listening.
Awesome. Great job, Mikhail. Thank you so much. You want to hop over to the next slide? It looks like we didn't have any questions right now, but if you have any follow-up questions, please feel free to put them in the survey after we hang up from this call. But first, I wanted to talk about our next session. This is the month of additive manufacturing for us. So our next session is going to be on June 21st. And the title for that session is Advanced Material Solutions and the Applications They Enable. We are lucky enough to have Chad Devine with us. So if that sounds like something you may be interested in learning a little bit more about, please let us know. You can go to our website and register there. And if you can't make it to the session, please still go ahead and register, and we will send the recording out to you. And it actually looks like we did get one question, Mikhail. Give me just a second.
Sure.
Okay, when using metal printing or the Metal X printing process, how do you design the honeycomb features? And that question is from Milton.
Okay, Milton. Well, basically, to design a honeycomb feature, there are 2 solutions to that. The first is if you're using any type of MIM technology or that uses 3D printing, or even SLS technology, which also uses metal powder, right? They are both sort of metal type printers. You can create that internal geometry using a software like NX or Materialize. Both of them allow you to create lattice structures within the software to create that structure. Now, Markforged specifically developed their own proprietary internal software called Eiger, and that actually creates a lattice structure within the part before it gets printed, and it's something that you can see live prior to printing your part. In fact, I'll actually, if possible, Andrea, we can always send you some information, and I can get you a trial account for Eiger.
Okay, awesome. Yeah, Milton, we will follow up with you on that one a little bit more. We did get another question from Deeptesh, and his question is, can additive manufacturing technology be used to produce parts at large production quantities like MIM process? Mikhail, are you still there?
I'm still here. One second.
Oh, okay. And while you're,
repeat that?
sorry, go ahead. Go ahead, Mikhail.
Andrea, could you repeat that?
Sure. So his question is, can additive manufacturing technology be used to produce parts at large production quantities like MIM process?
So I would probably say for the Metal X technology, probably not. It's more of a prototyping, I would say 10 to 500 part scale production process. It's to hit the market right in between what you can't achieve with traditional MIM technology, right? So it's not something to replace MIM, it's something to advance the process of MIM. Now, that doesn't mean there aren't solutions out there to hit production amounts, but I would definitely not suggest using something like a Metal X for mass production. Now, unless you could set up a farm for that technology, then that would be the only way to produce vast quantities.
Okay, awesome. I think that's all the questions at the moment. If you want to head over to the next screen.
Sure.
I'm sorry, the next slide. Okay, awesome. So if you are ready to take it to the next level, here at Saratech, as Mikhail talked about, we offer Mark Forged, HP, Big Rep, and we can help you with any questions that you may have about from our smaller machines to our really, really large machines. So please, there are no small questions. So please reach out to us if there's anything that you're wondering about as far as additive manufacturing. And then, of course, we offer engineering services as well to address your demand for any of your engineering needs. And thank you so much for attending. Please follow us at YouTube especially, and then all of our other social media accounts as well. On YouTube, if you register and you subscribe to our channel, then you will be notified about all of the videos that we post there. We have shorter videos, and we also have these CES sessions that we post there. So if you've missed any in the past, you can find them all there. And if you just stick around for about 30 seconds after this call, we do have a short survey, just a couple of questions. Let us know how we did today, and please enter any other questions or comments or any other follow-up information that you may need, and we'll be happy to follow up with you. We should be sending out the recording to this session today or tomorrow. Thank you all so much, and have a wonderful rest of your day.